find the area between the curve y equals pi x minus x squared times cosine squared x, and that's the solid line below, and the curve y equals x squared minus pi x times sine squared x, which is the dotted line below. Now, at first glance, this comes across a fairly like, how are we going to do this? Because we've only learned a few things. We know when we're looking for area, that's really something about integration. And we learned last time, integration, because of the fundamental theorem of calculus, which makes calculus fun, is all about anti-differentiation. But these two functions look very, very hard to anti-differentiate. And that's because they are hard to anti-differentiate. You're going to need tools that you're going to need from calculus 2 to anti-differentiate those functions individually. But let's not get too far ahead of ourselves. Let's go through the process. So when we're looking for area, the way we think about area, at least the way I think about it, is we go from the two intersection points, A to B, they might not necessarily intersect, but okay, so we're going from A to B, and then we're going to do top minus bottom and dx. So really the top minus bottom is just really a secret way of saying the height, and the dx is just the width, and I have height times width is the area of a small piece, and where my pieces are these little tiny thin rectangles. And then I'm going to add them all up, and that will find me the total area. Okay, so that's what we're after. So when we're given a problem that says find the area between curves, if we're not told what A and B are, we have to produce A and B. So the way we do that is we set the curves equal to each other. So pi x minus x squared times cosine squared x should be equal to x squared minus pi x times sine squared of x. And at this point, what we can do is we can say, well, if nothing else, a general good strategy is to put everything onto one side, so at least we have something equals 0. Because when we have something equals 0, that's a pretty positive sign. So I'm going to go ahead and move this part over. So we have pi x minus x squared times cosine squared of x, and we're going to subtract x squared minus pi x times sine squared of x. All right. Well, if you look at this, you say, well, pi x minus x squared minus pi x, they're basically the same thing. How do they differ? They differ by a sign. And we saw the sign, and it opened up our eyes when we saw that sign. So I'm going to put that minus through, so it becomes pi x minus x squared. So we haven't done much. All we've done is really take that minus and distribute it. And now we say, oh, whoops, we forgot equals 0, equals 0. Now it's like, look, these match. So that's pi x minus x squared. Factor out, you get cosine squared x plus sine squared x. And that needs to equal 0. But what's true about cosine squared x plus sine squared x? It's 1. So they intersect when pi times x minus x squared equals 0. Or, if you will, factor out x, pi minus x equals 0. So where do our intersections occur? X equals 0, x equals pi. 0 matches with the picture. And pi, that's pretty believable. All right. So there we go. There's our intersection points. Now you're probably thinking, you're in trouble, Steve. You've run out of space. But actually, we've done a lot of the hard work already. Because what's happening? Notice this part right here. This is the top minus the bottom. And we know that it simplifies to pi x minus x squared. So the area is going to be the integral from 0 to pi. And the top minus bottom becomes pi times x minus x squared, and then dx. What's the integral of pi times x? Pi over 2 x squared. The pi is a constant, so you simply take pi times the integral of x, which is x squared over 2. What's the integral of x squared? X cubed over 3. So pi over 2 x squared minus x cubed over 3. And then we evaluate from 0 to pi. So we're going to get pi over 2 times pi squared minus pi cubed over 3. And then we're going to subtract, plug in 0, you get 0. So that just goes away. Now you have pi cubed over 2 minus pi cubed over 3. And that becomes pi cubed of a half minus a third, which is 1/6. And so there's our answer. 1/6 pi cubed. All right. And again, I will say, if you only had to say, find that area, in other words, from this curve down to the x-axis, you couldn't do it. It's somehow when we combine integrals together. So be mindful. Sometimes when you have a problem, the individual parts might not be possible, but it's when you pull things together that nice things happen. So on to today. Today is a wonderful day because today we're going to talk about the substitution rule. And the substitution rule is probably the most important rule when it comes to doing antiderivatives and integration. So if you only know one rule, know the substitution rule. So where does it come from? Every rule for integration comes from a rule for differentiation. And this is the one that comes from the chain rule. So the chain rule says if I have a function inside of a function, f of g of x, and I take that derivative, then I'm going to get f prime of g of x times g prime of x. So now what do? You take the antiderivative of both sides. So if I take the antiderivative of this side, well, that's the antiderivative of f prime of g of x times g prime of x. And therefore, it's the antiderivative of this side, which is f of g of x, plus some constant. All right, so that's the idea. Now, how does this work? Well, essentially, the way that the substitution works is we introduce a new variable. And what we're doing is we're changing what we call our x, or really, we're changing our names. That's what it boils down to. And the reason we're going to do it is we want to get down to something that is simpler for us to integrate. At the end of the process, going all the way Calc 1 to Calc 3, there are approximately 10 integrals that you can do. And when I say there are 10 integrals you can do, there's 10 functions which you can find the antiderivative for. And that's it. We've already talked about 8 of them. We're going to add 2 more after this next exam. And so you might say, but there's so many more things out there, and absolutely there are. And so what we're going to be learning with integration is not learning, list of functions one after another. The goal is to find out ways to rewrite functions that we have to get it down to something that's on our list of 8 things that we know. And this is where substitution comes in. It's a way to simplify our expressions and get it down to something more condensed. So the way we do this is we say, okay, if I have an integral, say of f of g of x times g prime of x dx, what we do is we call this g of x, we give it a name, u. u equals g of x. And so that's going to become now a function of u. And then we say, okay, well, what's the derivative of u? Well, it's g prime of x dx. So we replace this g prime of x dx by du. And you'll notice I now have a function all in terms of this new variable, which should be simpler, more compressed, and I have a better shot of making progress. So we're going to be doing a bunch of examples today, but I think it's good to talk about some basic ideas, things to be aware of, things to look out for. Now, one of the biggest things that is a challenge is what's the right substitution? And how do I find it? And the good news is that there's 2 places to look. So oftentimes the function is trying to hint at what you should be doing. You just have to know where to look for the hint. So where are the 2 places? Well, because that rule for substitution comes from the chain rule, and that has a function inside of a function, the first place to be looking for where to make your substitution is say, do I see something that looks like a function inside of another function? If you do, that's a good candidate. So look for functions inside of functions. But sometimes that can be subtle. And so that's not the only thing you can look for. The other thing is if it's not clear what the function inside a function is that there's this piece here, g prime of x. So if you see something that say, oh, I recognize that, that's something that I have that I know how to integrate very easily. That can make a good candidate for saying, all right, what thing would give me that derivative? So if you can figure out what would produce that g prime of x, that's also a very good candidate for what to look for in substitution. Now, there are issues that come up. One of the things that you have to remember is that whenever you're doing a substitution, you always have to convert everything. Everything must change. In other words, if I started with my variables being x, and I'm going to a new variable called u, I can't have a single x left no matter what. Everything has to be in terms of my new variable. And if I can't do that, the substitution fails. So make sure you account for everything. And you might say, well, what if I don't have that g prime of x? Well, sometimes what you can do is you can manipulate and replace what should be a g prime of x in terms of u. And we'll do some examples to illustrate this idea. Another thing that might happen is you might have a very complicated function, and you might say, okay, I need to do a couple of substitutions, one after the other. Is that okay? And the answer is absolutely that's okay. It's okay to make multiple substitutions. Just keep track of what you're doing. So you might say, okay, so my first layer is u. Then we might say, what's your second layer? Well, you can go with w. And what if it's a third layer? Triple u. And you're probably thinking, triple u? What's that? Well, u, w, triple u, right? And then I've almost never had to go to quadruple u, but you could. No, you don't have to use these symbols, just any symbol you want. Remember, these are just names. Names can be adapted to be whatever's convenient at the moment. So use what's convenient for you to work with. Now, one other word about substitution is you are changing your name. And so at the end, after you're done, you've got to change back. Because I started with a problem in x, my answer has to be something in x. So I can't stop after I finish the integration. Then I have to work back through my layers. So we're going to do a bunch of examples, and hopefully this will illustrate these various ideas. Are there any questions before we jump into our examples? All right. Well, let us begin. Let's see how many we get through. So we're going to do our ones which aren't so bad. In fact, none of these are too bad. Find the integral of 2x e to the x squared dx. So, we're looking for a substitution to make. What's a candidate for a substitution to make? X squared. Now you might say, why is x squared a candidate? Well, look, x squared is inside the exponential function. A function inside a function. Is there anything else that suggests x squared is a good candidate? The fact that we see a 2x here, say, oh, that's a really simple function. I've seen that before. I've seen that's the derivative of x squared. Oh, maybe if I make x squared my substitution. So this is like double hinting. So it's like really, really strongly suggesting that we should try x squared. So in this case, our substitution is u equals x squared. Du will become 2x dx. So again, you just take the derivative of both sides and use the d notation, this differential notation. So change in u, take the derivative of this side, derivative of x squared is 2x times change in x. So when we make the change, the 2x times dx becomes d times u, du, and the e to the x squared becomes e to the u. And now we say, okay, we've rewritten this integral in a slightly easier form. Do we know the antiderivative of e to the u? Yeah, it's, what is it again? I'm sorry. E to the u plus c, because we want points. Remember, these are indefinite integrals. Put in your plus c's. We're not done. What needs to be done to finish up? Back to x we go. So we replace u by x squared. So e to the x squared plus c. And we're done. All right, well, it's a warm-up. We'll get some more fun ones soon. Find the integral of sine of e to the x times e to the x dx. Okay, what's our substitution? E to the x. Okay, why? Well, it's a function, e to the x, inside the sine function. All right, that's a good candidate. So we'll set u equal e to the x. What's the derivative of e to the x? E to the x. So we get that du is e to the x dx. So this part on the end, this e to the x dx, becomes du. So this becomes the integral sine of u du. Do we know the integral of sine? Negative cosine. So this will become negative cosine of u, and then plus c, because we don't forget the plus c. And finally, we say, okay, we've done the integration. Now we go back. And we say, all right, this becomes negative cosine of e to the x plus c. And that's our answer. All right. So far, these are pretty simple. This integration stuff, substitution, nice tool. Now here's a problem we could have done before. The integral of 3t squared plus 1 times t cubed plus t to the fourth. We could absolutely do this before. All we'd have to do is multiply it out, cross our fingers and hope we didn't mess up any of our algebra, and then do a lot of integration. So we could do it before. But now we can do it better. All right. Do we have a good candidate for a substitution? T cubed plus t sounds like a good candidate. Notice that t cubed plus t has two great things going for it. It's a function, t cubed plus t, inside a function, namely the function that takes something to the fourth power. There's something else that's great going for t cubed plus t. What is that? The derivative of t cubed plus t is showing up. So if you set u equal t cubed plus t, then du becomes 3t squared plus 1, then dt. So we get the 3t squared plus 1 dt will become our du. So this becomes the integral of u to the fourth, and then du. What's the integral of u to the fourth? 1/5 u to the fifth, because you add 1 to the exponent, so 4 plus 1 gives 5, divide by your new exponent, and of course we want our points, plus c, and to finish off, replace, so 1/5 t cubed plus t to the fifth plus c. So that's not so bad. I hope not.
Is it preferred to have the u to the fifth next to the whole fraction, or you can still put u to the fifth over 5?
You can put, there's lots of ways to write the same thing. Whatever you're comfortable with, that's fine. Yeah, 1/5 u to the fifth or u to the fifth over 5 are both acceptable. All right, I know what you're thinking. Come on, Steve, challenge us. We didn't just stay here to see the easy stuff. All right, let's do some challenge. Okay. Now, sometimes there's a substitution, but it's not so clear what to make. So you have to think about, what can I do to start rewriting things? So here's a problem. Find the integral of z to the sixth plus z to the fourth power dz. Okay, and now it's just like, Now, many of you, of course, are saying in your mind, that's easy, we just did this. We just will let u equal to z to the sixth plus z, right? Yeah? Because that's great, right? 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 What's the problem? There's no du term. See, there's this 6z to the 5th plus 1. Hopeless. Hopeless. Can't do anything. All right. Well, are we stuck? Do we have to expand this out? I mean, we can. I mean, it's possible. But we'd like to do things smart. We didn't come here to work hard. We came here to work smart. Okay. So, what's something we can do to rewrite this that might help us? Is there anything you can do to z to the 6 plus z? Let's start with that. You can pull a z out, right? So I can think of it as two pieces. So if I pull out a z out, I can really think of it as z to the 4th times z to the 5th plus 1 to the 4th. Right? Because I pull the z out, but it's still raised to the 4th power. True? Now, can we do something? People don't believe me. Okay, so the intermediate step, this is z times z to the 5th plus 1 to the 4th power. And now, that means each one gets to the 4th power. Now can we try something? Let's try, what's our substitution to try? U equals z to the 5th plus 1. And now du will be 5z to the 4th dz. And at this point you're like, oh, you were so close. So close, you don't have a 5. Ha 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 ha. Well, okay. So we have ways to fix that. Here's a couple of ways. I like to do the following. I like to call this technique divide by 5. So what I do is I divide by 5. And now I'm good. So I can say that z to the 4th dz is 1/5 du. Now if you don't like divide by 5, here's another way to do it. I can come up to this one and say, if I had a 5, life would be good. So what I do is I put a 5 there. And now life is good. But then you're saying, wait, whoa. You can't just put a 5 there willy-nilly. You got to compensate. So how do you compensate? You divide by 5. So you multiply by a 5th and 5 simultaneously. Multiply by 1 doesn't change anything, but now the 5 is there. Both ways are fine. You end up at the same place. So whatever you're comfortable with, that's what you should do. You should do what you're comfortable with as long as you're getting the correct answer and it's a true process. So let's put this together. We get that z to the 4th dz is 1/5 du. So I'm going to get integral, there's a 1/5. I like to put the constants in front, du. And then z to the 5th plus 1 to the 4th becomes u to the 4th. All right, so what's the integral of 1/5 u to the 4th du? We can start with u to what power? U to the 5th power. What's the constant? 1/25. 25. Why 25? Because there's a 1/5 already. And then remember, we add 1 to the exponent and divide by the exponent. So we have to divide by another 5. So now there's 2 5s. So that gets us up to 25. And plus c for all those points. Got to get them all. Okay, u is z to the 5th plus 1 to the 5th plus c. And we're good. Done. All right. Well, that's good. Kicking it up a notch. Got to like that. Next layer. Find the integral of dt over e to the t plus e to the minus t. Okay, that's not so bad. We can probably do that. Well, maybe we, what do we do? What's the function on the inside? See, sometimes it's not so clear. So let's think about ways we can rewrite this. A lot of integration comes down to saying, how can I rewrite my expression? What's something I can do to rewrite this expression to make it more friendly? I can bring the whole thing down to power -1. I don't know if that would make it more friendly, though. There's something else I noticed that I don't like. Notice I have an e to the negative t. What can I do with e to the negative t? What does e to the negative t mean? It means like 1 over e to the t, yes? So then at least the e to the t's look alike. So they're more compatible with each other. But I don't like that expression either. Because I don't like fractions within fractions. Okay, how can I get rid of fractions within fractions? I can multiply top and bottom by e to the t. And if we do that, I can write this as e to the t, because I'll have an e to the t upstairs. And downstairs, I'll have e to the t times e to the t, which I'll go ahead and write that as e to the t squared, and then plus 1. Now suppose we had this as our function. And in essence, we actually do have this as our function. It's not a different function. All we've done is given a different way to express this function. Is there a substitution here to be made? So we're looking for a u. Is there a good candidate? So where do we look? Well, we look for either a function on the inside or something where we say, oh, I know that's a derivative of something I recognize. I suspect an arctangent might be in our future, but not yet. So I would suggest that because I see this e to the t up here, I could think of that, oh, that might be like e to the t dt. That might be my du. If it were my du, what would my u have to be? U would have to be e to the t. So if I saw e to the t dt as becoming my du, because that's a good candidate, then u would be e to the t. So that would say that really I should be thinking of this as e to the t should be my inside function. And then du is e to the t dt. So this becomes integral e to the t du would be du over u squared plus 1. So, somebody mentioned arctangent a minute ago. Because 1 over u squared plus 1, that is on our list of 8 things we can integrate, because it's just such a beautiful function. What is it? Arctangent. So arctangent of u, add on your plus c, and finish up arctangent of e to the t, because we started with t. And that's it. We're done. So be aware, you might have to rewrite your function. You might have to manipulate terms. Now, let's really challenge ourselves. This is something else that we might have to do. Find the integral y cubed times the square root of 9 minus y squared dy. What can we do? What can we do? Well, we can replace the square root by a 1/2, but thinking about our techniques, what options do we have? Now, first off, is this something that we just can integrate without any problem? I think we have to work a little bit. It's not on our list of 8 things. 8 is a very short list. So we start looking for substitutions. Substitutions becomes essentially your big go-to tool. So if you're thinking about the process of integration, the process of integration is usually a pretty short process. It says, is it one of my 8? If it is, then you're done. If it's not, you say, okay, is there some algebra or maybe some trick? So you look for some way to write it, and then you say, okay, is there a substitution? That's the process you go through. And then after this, you take Calc 2. You basically just have these. Now, of course, it might be a feedback. You might say, okay, after I do a substitution, oh, then there's more stuff to do. But essentially, that's how you should think about it. Is it something that I recognize right away? Can I rewrite it in some easy way through an algebra trig? Is there a substitution to make? We're at this layer right now. Is there a substitution to be made here? Suppose you just said, look, I'm a very ignorant person about substitution. What's the substitution you make? Okay, maybe you're not very ignorant. Because you're probably like, oh, I know, y equals 5. No, that's terrible substitution. All right. Most of the people, when they look for substitution, they always think about, let me look on what's on the inside. The thing that's on the inside here is what's inside that square root. So the natural substitution for people to try is 9 minus y squared. So let's actually try that. That should be a go-to substitution. You should always say, let me try something on the inside first. And it may or may not succeed, but we try it. What does du become? Minus 2y, and then there's a dy. Now, the minus 2 is no problem. Constants are easy to move around. So minus a half times du is y dy. Now, at this point, we run into a problem. We want one y, because we want a y dy. How many y's do we have? 3 y's. That's like 3 times as many as we want. But let's think about what we have. Currently, I can think about, well, let me write this. I'm going to pull off a single y, and I'm going to move it to the end. So I have a y dy. So I say, okay, this y dy I'm okay with. That would be minus a half du. The square root of 9 minus y squared I'm okay with. What would that become? Square root of u. And I'll go ahead and do the calculus thing, put u to the 1/2. But we have to replace every single y. We can't just like, oh, I'll just replace half of them, and I'll call it a day. But we are allowed to use anything we know. What do we know about u and y? We know that u is 9 minus y squared. We are allowed to manipulate that expression. What can I do to rewrite this expression, u equals 9 minus y squared? Y squared is 9 minus u. And therefore, this y squared becomes 9 minus u. And now we're in business. We can replace everything in terms of u. So we're in great shape now. So the minus a half, I'll go ahead and pull that out. So we have minus a half comes out. This 9 minus u times u to the half. How would you actually go about integrating something like 9 minus u times u to the 1/2? You'd multiply it out. So it becomes 9 times u to the 1/2, then minus u to the 3/2, and then du. So that's what's going to happen after our substitution. And these pieces are easy to work with. And again, if you're wondering how did we get from here to here, I multiplied the u to the 1/2 through. So we get minus a half. Then we have 9. The integral of u to the 1/2 is u to the what power? 3/2. And then you multiply in front by 2/3. Because you divide by the exponent. Which is the same as multiply by the reciprocal. Minus, okay, u to what power? 5/2. Then multiply by the reciprocal, which is 2/5. And then put a plus c. And let's go ahead and just multiply this minus a half through. The 3 goes into 9. 3 minus a half times 3 times 2 makes this minus 3. U to the 3/2. Minus a half times minus 2/5 makes a plus 1/5. U to the 5/2 plus c. Are we done?
Oh, no, we have to put u.
Yeah, we got to go back all the way. Got to go back to where we started, where it all began, which in our case is 9 minus y squared. So 9 minus y squared times negative 3, 9 minus y squared to 3 halves, and 1/5, 9 minus y squared to the plus 5 halves plus c. And that's it. So we can do these problems. And, it just says, okay, when you make a substitution, make sure you account for everything. And you're allowed to use this relationship to rewrite and do your substitution. All right, let's try another problem. Find the integral 2t e to the power sine of t squared times cosine of t squared dt. So let's go ahead and do this slowly. So let's start by just saying, I see this 2t, I see a bunch of t squareds on the inside. We can set u equal t squared. What would du become? 2t and then dt. So this will become the integral of the 2t dt becomes du. Then we have e to the sine of u times cosine of u du. Okay? So we've peeled off a layer. But like an onion, there can be many layers. So what can we do now? We can substitute another one. So this will be another layer, w. What do we substitute for w? Sine of u. What will dw become? Cosine of u du. So this becomes the integral of e to the w dw. And now, see, what's happening is that every time we make that substitution, we're working on make it easier to work with, make it easier to work with, clean it up, make it simpler. Do we know the integral of e to the w? Yeah, it's e to the w. See, we got down to a place where there's it's one of our 8. Life is good, we can integrate. So, work our way back. Well, what's w? Sine of u. So e to the sine of u plus c. Oh wait, what's u? T squared. E to the sine of t squared plus c. And now we're good. Now you might be saying, couldn't we just have at the beginning made a substitution? One single substitution to rule them all. One substitution to bind them. And the answer is yes. You could have done that. You could have said, I could have said let u equal sine of t squared, and then you would have done it in one step. You'd get the same answer. So don't feel bad if you made it 2 steps or if you did it in 1 step. The goal here is to get practice. Practice in doing these problems. Practice in getting comfortable in carrying out substitution. And the more comfortable you get, the better you'll be able to do. And there's lots of interesting problems out there for us to work on. All right, let's try a nice cool down problem. Suppose A is not -1 or -2 or -3. Find 1 plus the cubed root of x raised to the power a. We're trying to find the integral of that. Now you might think, why did he tell us a is not -1 or -2 or -3? We'll find out why. I suspect by the time we understand, it's like, oh, that's why. Okay, so let's take a look at this. Well, is it one of our 8? It is not. So that means we have to think about things we can do. Now you might be thinking, well, I could do some algebra, right? Maybe I could expand it. But the problem is you don't know what a is. A doesn't have to be a nice number. It could be like a really weird number, like 6. Something strange. So we can't just expand. All right, so that's not out. That's not going to be something we're going to do. Okay. So algebra's out. It's not one of our 8. What's our last thing to go to? Substitution. Not surprising. I mean, this is to substitution day, right? We should be thinking about substitution right away. But you're going to see that substitution is just like the big tool. It's It's almost like the sledgehammer when it comes to integration. It's the tool that gets used over and over again. So what's the substitution to make here? Probably we should go with the inside. Now, I know you're probably thinking, Steve, yes, it's the inside part. Of course you would choose that. But another part of you is saying, I don't think that's going to work. Because if we set u equal the inside, now if we write this in our fancy calculus notation, that's 1 plus x to 1/3. What would du become? 1/3 x to the negative 2/3 dx. See now, the thing is, the 1/3 by now, you're like, Steve, I know how to handle 1/3. I've mastered the art of multiplying by 3. But there's no x to the negative 2/3. So we're stuck. Well, let's not give up hope too quickly. Okay, let's get dx by itself. So dx, I can rewrite this, so I'm going to move these two pieces across. So that would be 3 x to 2/3 du. Now, there's still a problem here. I can replace dx with this expression, 3x to 2/3 du. That's perfectly okay, but I'm not fully done yet. The problem is I'll have an x left in my integral. I can't have any x's left at all. So now the question becomes, is there any way for us to replace x to the 2/3 in something involving u? And it might help to note that x to 2/3 is the same as x to the 1/3 squared. So what can you do? X to the 1/3 is u minus 1. Oh, that's so nice. That's almost as if it had been planned that way, because it was. All right. So we get 3 times u minus 1. Oops, I forgot my square, du. So now I can replace dx completely in terms of du. All right. So let's see what we're at. We've got the integral. 1 plus the cubed root of x to the power a. What will that become? U to the power a, because 1 plus cubed root of x is u, so it's u to the a. The dx will become 3 times u minus 1 squared du. Now, u minus 1 squared, that is something we can work with, and that's something we feel comfortable working with. So, we can write this as 3 times u to the a times u squared minus 2u plus 1 du. Or, actually I can pull the 3 all the way out. And then I can go ahead and multiply this u to the a through. So that's 3 u to the power 2 plus a, then minus 2 u to the power 1 plus a, and then plus u to the a. Now the question is, can we integrate these pieces? Well, in other words, can I integrate u to a power? And the answer is yes. Now u to a power gets a little bit interesting though. Because if you remember the rules for integrating u to a power, we have that the integral of u to the k du, well, it turns out there's two possibilities. You either add 1 to the power and divide by that new power, but when does that work? Well, you shouldn't be dividing by 0, right? So this part right here works if k is not negative 1. What happens if k is negative 1? So you have u to the negative 1. What do you end up getting when you integrate? You get natural log. So you might say, wait a second, what if I have one of these exponents is negative 1? Well, if this were negative 1, what would be true about a? That would be negative 1. Well, a is not negative 1. What if 1 plus a were negative 1? A would be negative 2. Well, that's not possible. Could 2 plus a be negative 1? No. So see, that's why those assumptions were made. Those assumptions about a not being negative 1, negative 2, negative 3 come in handy at this point right here to say, oh, we have the simple rule. We're always going to be following this top rule because none of these exponents are negative 1. So let's work it out. So we have 3. U to what power here? So you add 1 to 2 plus a, what do you get? 3 plus a, and then divide by 3 plus a. Minus 2, u to what power? 2 plus a, divide by 2 plus a. Plus u to what power? 1 plus a, divide by 1 plus a. And then you tack on plus c. And finally, to finish this off, we have to go back to x. So we get 3 times 1 plus the cubed root of x to the power 3 plus a divided by 3 plus a minus 2 times 1 plus the cubed root of x to the power 2 plus a divided by 2 plus a plus 1 plus the cubed root of x to the power 1 plus a, divide that by 1 plus a plus c. Exactly what we would have thought when we started. Well, maybe not exactly, but we have a process, and the process works, and it gives us the answer that we need. So this is a really powerful tool. Now, let me just give you a 30-second preview of where we're going when we meet next time, which is, I know it's a little bit of ways. On next time, we're going to talk about substitution. Now, you're probably thinking, wait a second, you already talked about substitution. How could you possibly talk about anything else? Well, notice these are indefinite integrals that we've been talking about today. So next time we do definite integrals, and you find out those are even better. All right, that's it, and see you later.